So we're going to get started soon. So first of all, I wanted to thank you all for coming here. This is our first meetup, so you're all, like really lucky to see something awesome getting started here. My name is Marius, and this is Ram. So we are the co-organizers of this group. And the reason why we started this group was because, as some of you, many of you might know, I'm one of the co-organizers for the SV DevOps group. But I felt that at that group we do a lot of pretty cool stuff, but mostly theoretical. We felt that we're not doing a lot of practical things, and people really wanted to see like real stuff and talking about different technology. So this was the reason why we said this would be a great topic. And infracoders is actually an idea which was started by some guys in Australia, and we talked with them, and we wanted to do the same thing here. So today we're starting with a very interesting technology, which is CoreOS, Docker. So I know many of you, I chatted with you a little bit, you're excited about it, we're excited too. And we're going to continue to do the same thing in the future meetups. So what we want from you is to give us feedback. So let us know, how are we doing, what do you want to see. So for next month, we already have something set up. So that's taken care of. But afterwards, it's pretty much what we as a community will want to see. So just come, let us know. Or if if you're shy, just put in the comments on the meetup group or whatever. Just talk to us. So this is also the only time we're going to do a meetup here. Ram used to work for DT, Deutsche Telekom here, but they are going to move their offices out of here. So this is the only meetup which we're going to do here. And the next meetup, we're going to do it still in Mountain View at Cumulus Technologies. And like immediately, like tonight, we're probably going to announce the next meetup. So if you guys are interested, to know what it's about, the next meetup?
Yes, it is.
Yeah, so the next meetup is going to be about Netflix CI. So really excited hear about their open source technologies and how they use them. So it's going to be hopefully really cool. So before we're starting, I just want to say thank you to Anthony and Internet for making this possible from the sponsorship point of view. So it was a last moment, and he jumped into it, and helped us with food, pizzas, drinks. So thank you so much, Anthony. Thank you, Internet. If you want to come, say a few words, that would be awesome.
Yeah. No, hey, thanks, guys. I appreciate you guys having us. Internet is an infrastructure as a service company, and we're sort of in the very kind of early stage, exploratory stages of using CoreOS and Docker. If you guys have any projects you're working on, we're always kind of curious to talk to you. Feel free to email me. I think we can, or just get in touch with me afterwards.
You can come talk to him.
Yeah. Feel free to just say hello, or you can just tell me what you're working on. Always kind of curious to see what people are working on.
Yeah, you guys should go say hello to him after the meetup. All right, thanks, guys. All right, so the format of the meetup today is going to be like pretty flexible, and it's going to be like we were not sure what we're going to get, but we have Brian here who's from CoreOS, and he has all the freedom to do whatever he wants. I just told him
and the responsibility to show useful things.
But I told him he needs to show us cool stuff. So I'm sure how many of you are using Docker? Oh wow. Okay. So how many of you are using CoreOS? Okay. So that's pretty good. So
I have a quick question. How many folks have built a Docker base image from scratch so that they never needed to touch the Docker hub? That's what I'm looking for.
Yay.
Everyone here, by the time you walk out, will also know exactly how to do it and will have seen a method for doing that. So.
Yay. All right, so without further ado, I'm gonna let Ryan do his thing. We're very excited to have you here. Mm-hmm. Thank you so much for joining us. We're really excited about CoreOS, and looking forward to see your thing.
Awesome. to be up on it. So, my name is Brian, aka Redbeard. I am from CoreOS. I will start running through some of these here. So, some of you may have seen portions of this slide deck before. Other folks, unless you were in Florida last week, you know, a lot of it, some of it will be new. I used to look like that back when I worked at Red Hat. I put up there that my title is customer-facing guy at CoreOS, which is, you know, we're talking minimalist Linux here, you know. So, and yeah, trademark Linux, fancy stuff. So, let's see, up, and of course, LibreOffice crashes. So, that is the way it goes. So let's go ahead and get LibreOffice brought back up. Yes, I would love to recover that. Recovery in progress. There we go. So back to the correct actual presentation. We are off to a wonderful start. I realize that I am in the minority of folks who actually ride the metal and run Linux on the actual desktop. So, you know, I used to have a beard like that. I got tired of all the Duck Dynasty comments. So, you know, what we are here, or what I actually do, you know, my official title at CoreOS is Principal Architect. That's really just a fancy way of saying that I handle everything from consulting to customer service to technical support, and as of a few days ago, I'm now doing documentation. So we have a lot of different things to cover. I know that there are some folks here who are familiar with CoreOS, there are some folks who have not touched it, and then we've got probably some subset of folks who are looking more just at some mechanism for running Docker. So what we're going to start out with here is this one over here, which is talking about what CoreOS is and what CoreOS is not. You know, we've got a bunch of time, so I will go into great detail on actually bringing up clusters, but we'll get some of the folks who are not familiar brought up to speed here. So CoreOS is not Chromium. It's not Chromium OS. It's not Chrome OS. It's not CROS. It's not a fork of any of those. You know, what is happening here is, I don't know if anyone has built a Linux distro before, but the hardest part about that is the bootstrap phase. And I keep popping in that. So I'm just going to talk real loud here instead, because I have a giant mouth anyway. So, you know, the hardest part of building a Linux distro is the bootstrap phase. You know, it's coming up with the actual toolkit that you're going to use to build it. And the folks over at Google had already built a wonderful toolkit that they used for Chrome OS. So we said, awesome, that's open source. We're going to take that and build on it quite a bit. And we've done a lot of modifications, and that SDK is up online, and we have documentation on how we actually build CoreOS from scratch up on our website. But where we started with this is that we wanted to secure the internet. Real lofty goal there. So if we were to take a look at a similar type of issue, HTML5 started its ratification process in 2008, and the proposed deadline was 2022. And then in 2020 or 2011, that date was revised back to 2014. And the mechanism that they did it, the mechanism for why HTML5 was ratified so much more quickly than what was expected, was that browsers started forcing out updates. The browsers figured it out here. You know, the idea is that in the course of 3 years, that total deployment was reduced by half, and we thought, what would happen if you started doing this with other application components as well? So in April, when Heartbleed came out, we had 80% of our systems that were using CoreOS patched in 3 hours, which the consulting customer who I was working with at the time, they had a freak out, because they had OpenSSL embedded in a lot of their applications on their consumer electronic devices, which many of you have in your home. And they had to figure out how they were answering this as an entire organization. So they said, Redbeard, don't come in till 11. Our morning is real busy here. Not a problem. We're updating all of our customers too. I get in there at 11 a.m. First question, how do we update everything? First answer, it's already updated. You obviously didn't look at EtsyOS release. They're all confused. They go and log into the boxes. The boxes had been patched and taken care of, remediated without them even noticing. Now, this is not to say that, there is an answer for automatically pushing out all these updates to Docker containers. That is not a directly solved problem yet. There is artwork in the community about how folks have done this, and we'll talk about that a little bit. But the way that we actually start doing all of this, the way that we actually achieve this is first, we containerize all of our applications. For most of you, that's probably going to mean Docker. It does not require you to use Docker, though. We also ship another containerization type called systemd nspawn, which I will show you here, and I will make sure that you're intimately familiar with and show you why that's useful for troubleshooting. The next step is that we have this self-updating operating system. It's funny, because that's one of the things that folks get the most excited about, and for a lot of us at CoreOS, that's the least exciting component. Because it's just Linux, and we kind of stuff this Omaha protocol stuff in all together, but the things that get all us excited is etcd and Fleet and all of the kind of distributed systems tools that we're building. And that's exactly what we're talking about here. Everything from making sure that you can write a value into this key value store and every machine will know immediately that it's there. Making sure that if you have some process that needs to be run on a cluster of machines, that you can dispatch it and guarantee that it's going to be up and running somewhere. Also now we've released a tool that works with Kubernetes called Flannel, which is a software-defined networking component to be able to guarantee that you have a consistent IP space across all your machines regardless of the cluster that it's running on. This is the kind of stuff that gets us excited. But we're going to talk about each one of these real fast. Application containers, like we said, that's basically going to be Docker. The idea was that for most Linux distros, this is the world you live in. Everything over there is what they manage. This is what they want you to manage. They don't want you to touch Python, because if you touch Python, you break Yum, and you break all of the other utilities that they had. But my apps depend on a specific version of Python, and I don't want to live in the past. I don't want to be stuck in some world where I can't easily install a new version of Python and use it, or where they're locking me back to an old version of OpenSSL that doesn't ship like K-curves for elliptic curve cryptography. No P-curves, I mean, don't want those. Don't want NSA actually looking at my stuff, but K-curves, great. And awesome, you ship MySQL 5.1. That's been around a minute. I'd really prefer to use something new. So we took a look at the containers, and the idea of containers was that you shift that line of what a distro is, and these are the things that you package together that actually make your application. You care about the version of Python. You care about the version of Java. So why not include it with the application? And at that point, why not just strip all of that out of the operating system so that you don't have to worry about patching that, so that you don't have to take the system down fully to patch that sort of stuff. So on the back end, we've got this thing called Omaha Protocol. It just is this method for us communicating a small amount of telemetry from systems so that we know the state of an update in process. If we go to push out an update, for example, I think it was this morning we pushed out an update for version 444, we can actually see, are machines successfully updating? Are they stepping through the entire process? Are they failing? We have had issues in the past where systemd pushed a new version, didn't update everything in their change log. We suck it into master, we push it out to host subscribe to master, or system subscribe to master, which hopefully is none of you. We only expect to use that for testing. But we push this image out to master, and the machines all start faceplanting. But what we do there, what we have with the update server, is this process where we know about the state. We know if a machine has downloaded an update. We know if a machine has applied the update. We know if the machine has rebooted for the update. And we know if the machine has reverted back because an update failed. And that's what this whole process of Omaha is doing. But that's really just the transit of getting an update down to a system. The way that we actually do it is there's a whole GPT partition table on the box. GPT, the GUID partition table. So we have GUIDs defined for different partition types in the same exact way that there's a GUID defined for a FreeBSD partition. There's a GUID defined for a Windows modern partition type, Windows 8, Windows 2008, etc. And what we do is we have this system with an A and a B partition. These are the only ones that we touch. This is what gets mounted read-write on a box. These are mounted read-only. And this is where the core of the operating system actually lies. So in this case, we are running off of our A partition. Omaha has said that there's an update, and it will come down, and it will get applied to the B partition. Assuming that that update is successful, and that we reboot, and that update comes online, great. We are now running on the B partition, and we just keep going from that. If for some reason that update were to fail, though, we revert back to the A partition, which we were running from before. So we know it's a known good copy of the operating system. So that's how we're able to push out these updates and have a high degree of reliability that that update is going to succeed. Now, for anyone who thinks that this may be some kind of black magic or witchery, I can't really claim any, can't claim that we pioneered anything here, because this is what load balancers and consumer electronic devices have been doing for 20 years. This is not anything new. People were paranoid back then. We just took a look at it and said, we could probably make the bootloader do that. And I would really prefer to be running my OS user land in a read-only state, so let's give it a shot. And it worked. So we've got this idea of a kernel and a user land which updates itself. The next thing that we build on top of that with is systemd. Systemd is a very polarizing thing for some people, especially folks who have been using POSIX-type operating systems for a long time, because it does a lot of stuff. It will give you an init system and a logging system and this concept of cron, or their version of cron, and a resource manager and IPCs through dbus and a simplified configuration. It also gives you this coordination thing. So coordination is done through a mechanism called targets. Targets are similar to run levels. Run level 3, which is your general multi-user with networking, that corresponds to the multi-user target. Now, the idea with targets is that you can be in multiple targets at the same time. I can be in multi-user, but not networking. And also, because there are these targets, you can base services to load on when a target is in place. So the idea is, I can say, Docker shouldn't start until the networking target is online. It doesn't make sense to have it, because it expects to call out and do a bunch of network operations. Additionally, like we said, simplified configuration. You're not really going to be able to see the detail, but this is a startup script for Logstash. Logstash is a wonderful product, and in this startup script, we've got a bunch of preamble just telling various Linux distros how to handle this init script. So we've got a little bit here for LSB, Linux standard build type. We've got some stuff up here so that check config handles it correctly on Red Hat. And that's all just, probably 15 to 20 lines of comments just to get everything set up before we even start defining any of our variables about where Java is located to get things online. Over here, those 4 lines define the user that we want to run as, the group that we want to run as, the command that we want to run, which is just saying, hey, run user local bin logstash, and set this environment variable of Java mem 256. It's much, much easier to write startup scripts for systemd. And we'll see that because we'll have to write some for Fleet. So when I start banging out on systemd, by all means, folks, raise hands if you got questions. Now, this one's going to be a little bit of a long one where we're going to switch to a different slide deck where I can go into a lot more detail on etcd. So what we have here is etcd. The idea of etcd, and as initially conceived, is that your etc directory distributed throughout an entire cluster. Again, lofty goals. That's what we're all about here. So the key things that you need to know about it, if you were to only remember 3 things. 1, it is highly available. It is a highly available key value store which provides locking mechanisms for distributed applications. Highly available, key value store, which is a locking service. The other thing that's nice about it is it's very easy to deploy. So for anyone who's tried to set up Zookeeper, it is a non-trivial task to have Paxos doing automatic replication between all of the Zookeeper nodes. With etcd, it is pretty simple. You can use one etcd cluster to bootstrap another etcd cluster, so you can have this chained bootstrapping mechanism in place, and we run a public-facing etcd cluster exactly for that purpose. So we're going to skip here. So why would you want a highly available key value store? Well, when you get to the scale of reasonably big companies, you realize that building distributed systems is hard. In other words, you can't have 100,000 servers without a traffic cop. Well, I'm not a big fan of traffic cops. And well, Zookeeper's a competing product, so we'll skip that. You know, you need some source of truth here. You're going to have a bunch of systems. You need to be able to guarantee that the values and the configuration that you're setting are available across all of them, and that's what we're doing here. It's this component that sits in the center to guarantee that everything is kind of consistent. So, how does Google do this? Well, sorry, how does Google do this? Let's play nice. They do it through a tool called Chubby. Now, I will say that the 13-year-old boy in me giggles when it's that, but it loses a lot of the reaction when it's just giant on a screen like that. You know, it just becomes symbols and not an actual real world. But Chubby is the Google answer to those types of services. It's primarily a locking service, but it also provides some file system type semantics for interacting with it. And you know, Mike Burrows summed it up as such. The purpose of the lock service is to allow clients to synchronize their applications and agree on basic information about their environment. This is pulled directly from the Chubby paper. I don't know how familiar folks are with the historic model of open source at Google, but the historic model is, we have this brilliant idea, we wrote this awesome software, we're not giving out the code. We will write an academic paper, we will detail all of the algorithms, we will make sure that all of the mathematics are sound and that it is welcome for anybody who wants to implement it. So they published this paper on Chubby in 2006. They presented the findings at Usenix, and that kind of spurred other folks building similar things. Now, in the case of what it's actually used for, services that elect a primary something, doesn't really matter, you know, services that partition data. In each of those cases, you need something to actually advertise all of the individual results. And that's what we started doing with etcd. We took a look, we read this Google paper, we said, that's a brilliant idea. How about we build that? Oh, they're talking about Paxos, and they get into multi-Paxos, and they even admit that their implementation has some holes in it. And then Diego Angaro, PhD student at Stanford, published his paperwork on Raft. The whole point of Raft here was to kind of cover, basically give you an easier to understand version of Paxos. So what we've got under the hood of etcd is an application written in Go, which means it's extremely portable, based on Raft. So what we're going to do here, we're going to talk a little bit about Raft. So what you need to know about Raft is that it's a consensus algorithm. That's not Paxos. But before we even get into that, how many folks here are familiar with or have built distributed systems? Oh, more than I expected. Well, for the folks who are not here, or for folks who have not done that, we're going to define a few terms. And, you know, I do not come from academia traditionally. I am a good old-fashioned high school dropout who decided to teach myself a lot of this stuff on the fly. So please pardon me if my definition of these terms does not completely line up. But we start out, there's two things that we need to know: consistency and consensus. The idea of consistency is that you want to know the degree of difference between two members of a system, the level of the guarantee that the data will be the same no matter who you retrieve it from. Additionally, you want to know about consensus. Do all of the members of a cluster agree on who the leader is? Who has the state machine been replicated, etc.? So Raft specifically implements sequential consistency. He refers in the paper to eventual consistency, but the real-world implementation of what we have built is sequential. And it's achieved through write serialization. So in other words, you have an append-only log, you serialize all of its write operations, and that gives you a deterministic state machine. Again, I'm a good old-fashioned dropout. That doesn't mean anything to me. So the TLDR is we get a guarantee that a get of index X will always give us the same result no matter who it is in the cluster. So, what does that look like? It means that when we have a cluster of machines and we have two requests of a put of A equals 1 and then a put of A equals 2, that the data does not actually converge until a majority of the machines have that set. So, basically what we're looking at is over here on the side where we have the values that are actually set. And this is very dry, and this is very boring, and that's why I can't wait to get into things where you actually see this in action. But, I just wanted to make sure that everybody's on the same page here. We've got a level set. So we have a consensus protocol. The consensus protocol links together a number of machines. Where does the key value store come into play? Well, the API for it is based on HTTP. So we tried to pull as many of the verbs that matched well to things in Diego's paper and make sense of them. So, put a value, get a value back, delete it. If you are not the type that wants to deal with all of that, you can use the CLI utility. Or there are Go libraries, and there's Java libraries, and there's Python libraries, and Node, and Ruby, and C, and C++, and Clojure, and Erlang, and .NET, and PHP, and Haskell. And really, if there isn't something that you want to interface there, and yet you need to use etcd, I can't help you. You're a little bit beyond help. You're wearing 2 pairs of socks and sandals, and, I have to kind of let you be you, and you can hop on IRC and ask some questions. But so let's also take a second to talk about what folks are doing with etcd. We've got this thing built into the OS. We've got this thing that runs on Mac OS and on FreeBSD and just about every other POSIX system I've ever seen. What do folks actually do with it? Well, the folks over at Rackspace built a TCP reverse proxy using it. Folks over at Skynet built a DNS server for service discovery. Different folks have built configuration management tools. Other folks have built orchestration tools. So you see that the Cloud Foundry folks have begun using it in the rewrite of their core, which is Diego. And then also, we see that Google's using that. So when Google open sourced Kubernetes, they chose etcd for their storage engine because it was the closest thing to Chubby that existed and was simple to deploy in the kind of open source arena. So we're gonna go ahead and get our demo, or one of our demos, set up here. So what I am doing here is I'm gonna pull across this page, and I'm just going to go to CoreOS.com to start. So you're sitting on the home page. Right down here, we have this download CoreOS link, and slightly unfortunate, there's this little arrow here. This has the directions on setting it up via Vagrant, or Pixie, or iPixie, or your cloud provider of choice. We're going to start out, and we're going to do EC2. So I do that. First thing they say is, hey, choose a channel. I love living on the bleeding edge, which is not that bleeding. Because here's the other side of that coin. We get folks all the time going, so I heard that there's some awesome new features in Fleet or in etcd. How do I get those into stable? You chose stable, so you wait for them to get to stable. If you want new shiny, you should use new shiny. And we run all of our infrastructure on alpha. We drink our own champagne on that. I used to say we eat our own dog food, and then, my fiance pointed out that I'm comparing our product to dog food. So we drink our own champagne there. So what we are going to do is we are going to go down to US West, and we're going to say, hey, launch it. And this is going to pull up all of the stuff in a cloud formation to make this as simple as possible. So this is going to be the cluster named Redbeard Infracoders. And then we say, yep, that template is just fine to use. Let's go with it. Now it's going to ask for a few pieces of information. So one, and I guess I should also verify that in this region my keys are actually in place. Always good to verify this stuff before you fire it off and then go, hey, why is my stuff not working? And I'm glad I did, because I need to actually import that. So, pardon me 1 second while I say cat sage ID, or say, yeah, not my private key. I mean, I trust that nobody's going to be able to really copy and paste it that quickly, but why roll the dice? Okay, we're going to call this B current import. Okay, so now I know that that's going to work. So we're going to use private IP addresses. We're going to allow SSH from everywhere. We're going to say, give me a cluster of 3 machines to start. Now, it says here, give me a discover URL. Like I was saying, bootstrapping etcd is easy if there's already an instance of etcd up and running. So that is why we run discovery.etcd.io. And if you give it that path of new, it will respond back with your own unique discovery URL. So we take that, we pull it. I have a bash alias just because I do it so much. And we're going to do 2 things here. One, I'm going to load this so that you can actually see what's there. Really, it's just saying it responds back with nothing. There's nothing inside of it. And then we are going to, okay, we got that. Specify our key. And then we say, hey, go ahead and launch. Yeah, I don't need any of that. And we go ahead and say create. And here in the list, momentarily, we will have showing 5 stacks, create in progress, Redbeard Infracoders. So we'll let that sit for a second. And one of the things that I will actually do also in the background here is I will pull this up. Oh, small. Oh, well. I'm going to say watch-n1 curl. No. Python. Come on. And JSON.tool. Ah, thank you. Now I understand what you meant by input. And let's just make it a little better. So what you will notice here is as the machines actually come online, you will see the entries get added to them. Like we said, what this is this is an instance of etcd that just provides that extra quorum vote, basically, and a mechanism for all of the machines finding each other. I explicitly wanted you to see this and see what we see on the back-end side. So there, those nodes came online. They said, if you want to contact me for server communications, that's the address you want to talk to. Here is the index that we're actually sitting at right now. That's the TTL on this key. All of the keys that are written to discovery.etcd.io have an automatic TTL set on them of 1 week. That means that should you decide to spin up a machine, and should someone discover what your key is, the only things that they will be able to see is the private IP address, this 172.31 address, which chances are folks are not going to be able to hit, and it's going to expire after a period of time. The only time you need that is when the initial cluster is brought up. After the cluster is online, after the cluster has reached quorum, that is useless. You don't need to touch it ever again. You can just forget about it. It will reap itself, and everything is done. So, what we have here is actually 3 different entries in that, and I do the JSON so that you can actually see it. So we can tell we have 3 machines online. And this is the coordination key that they're using. Make sense, everybody? I realize that it's this, we have to build a virtuous cycle of he just keeps talking and none of this completely makes sense. So, I kind of have to lay this groundwork, then come back to it and keep pivoting a little bit. So, but long story short, at the moment, we have this cluster up in the background that we can come back in a few minutes and actually do stuff with. So, let's try to see if we cannot get that back in place. So, we got that set up. The idea here, though, when you're using some consensus algorithm, especially something like Chubby or like etcd, is that you want to keep it relatively simple. Also, important point that's not immediately apparent to folks. Consensus algorithms were not generally designed to be run over a WAN. So let's talk about this for a second. Here's where we're at, roughly. You have a data center in Dulles. You have a data center in Oregon, where we just brought that cluster up. Everyone does realize that there's 90 milliseconds going on between that. At least, yes, that's, kind of if you're lucky. So if we think about this, the default heartbeat in etcd is 50 milliseconds, and the election timeout is 200 milliseconds. So you can do that, but your likelihood of missing heartbeats is pretty high, and your likelihood in the worst case scenario of losing quorum is even higher. Now that being said, the RAF paper suggests that the heartbeat be set an order of magnitude higher than your election timeout. In practice, we normally use about 4 to 5 times. That's unfortunate, it wrapped it a little bit, but we've got that all documented in the tuning section of the etcd repository. Since messages are not committed until a majority of the nodes have the message in that log, that was kind of the A equals 1, A equals 2 thing that we showed earlier. That means that in a cluster of 5 peers, a write operation will only be as fast as the 3rd fastest machine. High availability does not mean high performance. They're not mutually exclusive. It's just that if you make poor design decisions, that might bite you. We're doing things with a write-ahead log, as we mentioned before. Write-ahead log uses the disk. And a T1 micro disk is not especially fast. It's definitely disk as a best effort service. So that means that if you're in a situation where etcd is constantly expecting to write these heartbeats and all of its data to disk, and your disk is really slow, etcd is going to be really slow. And if etcd is really slow, and you lose heartbeats, etcd loses quorum, and then nobody's happy. So what we're going to do is we're just going to cover a few quick operations tips and developer tips. Just, they're things that if you know this going out of the gate, your life is so much simpler. 1, use availability zones, not regions. That's why they're there. Availability zones are to make sure that you have that redundancy that you're looking for without introducing 90 millisecond timeouts to things. Keep it to 5 nodes, or at least some odd number. And keep in mind that this is what we're talking about here is for the purposes of maintaining quorum, for the purposes of maintaining state, guaranteeing that your data is actually online. If you're in a boat where you're worried about running 9 machines because you think that the likelihood of 5 or 4 of those machines going offline is very high, the problem is not likely with etcd. You may have problems with your infrastructure that you actually want to look at. Because remember, in that case, if you're running 9 nodes, it's only going to be as fast as the 5th fastest node, which means that things are going to be slow. That's why using those availability zones, maybe it's something where you run 2 nodes in one availability zone, or 2 nodes in one availability zone, 1 node in a 3rd, or a 2nd availability zone, and 1 node in a 4th. It shouldn't be hard to keep, actually we'll do 3, 2, 1 there. 3, 2, 2, yeah. We'll do 7 nodes total. Doing it in such a way means that you cannot maintain quorum without 2 entire availability zones being online. But if you lose an entire availability zone, you're still set. You lost that entire location and everything is cool. The other point there, though, is that if etcd loses quorum, your data is still there. You just can't change it. That means that things might be stale, but they're still online. And speaking of things being stale, always, as a developer, try to know the index that you want to do a read for. There are some cases where the most important thing is to be fast. If the most important thing is to be fast, read from the cluster and just work with what you get. At that point, you can read from any of the nodes. And you don't have to necessarily worry that the master has committed that to all of the individual nodes. If what you're looking for is a guarantee of being absolutely correct, then look up the current index from the master and then read that index from one of the nodes. Also, learn to work with loosely coupled systems. Things go down. Werner Vogels famously said, everything fails all the time. If you kind of learn to live in that sort of a world, then part of your etcd cluster going down, part of losing a network link, losing an entire availability zone, losing an entire region, they're things that you can generally recover a little bit better from. Also, use your lock to elect a primary, not store all of your data. I've done a lot of performance testing with etcd, and I'm about to publish a bunch of those results. The big thing is, quite obviously, if you've got keys that are on the order of bytes or kilobytes, they are faster than on the order of megabytes or tens of megabytes or hundreds of megabytes. You can write 100 megabyte keys to etcd, but keep in mind, 1, the master is now going to write that to disk, and then the master is going to transfer that 100 megabytes out to every one of the nodes participating in consensus, and then they're going to write that to disk, and then they're going to respond back to the master, and not until a simple majority of the nodes have said, yes, I've written that to disk, are you going to get a confirmation back. Because every time you write something, it has to sync down to disk and come back. And the reason for that is to guarantee that your data is safe. Yes?
What kind of keys are like tens of kilobytes or megabytes in size?
So, for example, let's say that you had something where you were electing a master. Like, let's go one step further, and let's say you were running a MySQL Galera cluster, because folks from Rackspace actually just published a thing on this. You have an entire Galera cluster where, first off, the nodes need to find each other. So when each container comes online, they look and see if etcd is available, and if etcd is available, they write their location to a common key space. Now everything that's reading that key space, similar to that discovery URL that we used, will be able to find all of the etcd nodes, and now they can begin to coordinate together to find each other and say, hey, everything's good to go here. So it's used also for service discovery in that way as well. Possibly it's something where you have a group of systems where only one of them can handle receiving writes, but all of them can handle receiving reads. That allows you to take a lock in such a way where you say, I'm the master, I'm the one handling the writes at the moment, but here's a list of everybody who can handle reads. Does that make more sense?
No, I think my question was a little different.
Okay.
When you say the key size can be like megabyte or even more, right? What kind of a key can be of that size? Keys are typically smaller, but their corresponding data is generally larger, right?
Yes.
So in what case your key itself is such a big key?
Sorry, the value in each case. You can set a megabyte
okay, sure.
for
The value is itself.
yeah. So what we are going to do is now we're going to bounce back. Actually, what we're going to do is we're just going to directly log into this host and start kicking the tires on it. So let me. Folks have questions thus far. That was a good question. Yes.
So the majority, once the majority is done, the value can be read. What happens?
Yes.
Remind me, they fail to retries or something.
Yes. So if you have a node, or let's say that a machine loses quorum, goes away, and then comes back. What happens is the master is going to find out what the current index is of the host that went away, and it's going to go back and start replaying that write-ahead log, that wall file, to the host down there to make sure that it purges anything that wasn't committed, things that, maybe if it had primarily been the master, but that the things that it had in its queue hadn't been fully committed, it knows how to go through, reap all of those values, and then go through and start playing back that serialized journal to make sure that it gets caught up. Does that make?
So if things go out of CoreOS, right? So let's say the node is still alive, but one of the write failed. What happens? So it's retrying until the heartbeat is all fine, but this entry didn't.
So if you go to make a write to it, and the node that you are attempting to write to has lost quorum and doesn't know where the master is, it will return a 500 error, letting you know that it was a permanent failure and that it does not have quorum, so you should not attempt to write again.
No, you 5 out of 10 succeed. The remaining 4, we don't know.
So in that case, so let's use 5 nodes as an example. You have 3 nodes that are still online, and these 3 still have maintained quorum, and then you have 2 nodes in a different availability zone. Everything in this other availability zone is reading from that, but when they go to do the reads, there is a header that comes back that says that things may be stale. So you're still able to read the data back, but any attempts that you do to write to that cluster would normally get redirected via a 301, I believe, to the master, because only the master can actually commit data to that. So it will attempt to commit that data. You're next, so I want to make sure that you don't tire out there. So you attempt to get redirected to that, but the nodes, if they know that they are not the leader of consensus, will not attempt to actually commit anything to the journal. So, also, one thing there, if you are interested in any of this, Raft Consensus. So raftconsensus.github.io is Diego's page where he covers a lot of this, and he has an entire simulator on here that will allow you to test failing nodes out of the cluster and slows down the election process by some factors. So, if watching these beads go back and forth at 50 milliseconds a piece is a little bit fast for you, then you can actually slow it down and watch as the elections actually occur. I would also highly recommend, if you're interested in this, reading the Raft paper, because it's surprisingly understandable. And if a Yahoo like me can make sense out of it, then everybody in this room can definitely do it. So, yes, your question in the back.
So for receiving rights,
Uh-huh.
when I move to receive rights, there is a implied wait for it to complete, or
So if there is an in-flight read, if you have requested an index, so let's say that I'm reading from this node over here, and a write commits but hasn't gone over, if I know the index from over here and I attempt to read it and provide that index as a part of the read, it will actually wait until that read is committed or time out. So you know that you can request that, and it will hold in a like an HTTP long poll, waiting for it to be committed, and then as soon as it gets it, it will respond.
right when you do this thing, but for the reads, if you wait for the reads to complete, then you might increase the latency for write.
Well, so the reads or the writes always start at the leader and are committed there, and then they're propagated out to. So it depends on if you want a consistent read where you are forcing the most up-to-date copy, in which case you can actually redirect to the leader, or you can look up the leader first and query directly from that. But if you do that, you have the potential to have all of your nodes start clobbering the leader, which then, yeah. Yeah. So, let's get logged in. Any other questions?
If you
Yeah.
want to take one more quick question.
I will take his, and then we'll get to yours. Yes?
My question is on discovery. Any plans to add other discovery mechanisms?
So, yes and no. The folks over at SkyDNS wrote the DNS portion of it to handle that aspect of it. We really wanted to focus on the consensus protocol and the basic key value store, and make sure that it was easy for anyone who had a particular idea in mind to be able to implement that. The one pet thing that I would personally like to see for that is instead of using the discovery component directly, I would like to see the ability to provide an SRV record, just so that in an enterprise environment where you already have a very strong DNS infrastructure, you'd be able to specify the hosts and the port and any failover for that. But beyond that, we don't have any direct plans to. So the idea is definitely more the like SkyDNS did. If DNS reading and writing or if DNS reading of keys out of the key value store is what you're looking for, there are folks who already are working on things like that. And then your question.
So when you say a write is committed, only when the write is committed on a majority of nodes, right?
Yes.
There are two questions here, right? Okay. Is this majority defined by different set of nodes for different writes, or does it have to be the same set of nodes for all writes?
It's going to be this. It's a simple voting procedure. So if I have a value that I want to commit to the journal, and I go ahead and write that to the leader commits it to its log, but doesn't, or sorry, the leader writes it to its log, but it doesn't mark it as committed in the journal until, n plus 1 or n over 2 plus 1 number of nodes respond back to the leader saying.
It can be any different nodes.
Yeah,
right?
any different nodes, yeah.
Sounds good. And when you're talking about majority here,
Mhm.
why you are at least requiring it has to be odd number? It could be an even number too, right?
Because if you have a network split, you will lose quorum. There's no way to have a leader in that case. So if I have 2 nodes on, we'll make this worst case scenario. Let's say I've got 2 nodes running in Oregon and 2 nodes running in Dulles. If I have a network split, no side is the leader. Like no side can actually resolve who should actually still be able to maintain the quorum
It can
there.
happen between an odd number of nodes when one node is down on like a stable network. It can happen. Right? It's just theoretically, right, okay, it doesn't change the scenario as such, right? I have 5 nodes, for example.
Yep.
Say one node is down and then after that the network split happens. That's it's the same thing. You're defining your quorum by majority, right? Okay.
Yes.
So if the network split happens, like okay, 3 nodes in one network and okay, 1 node in another network, then okay, you're fine. Even with 4 nodes, right? So
Yes.
when you're looking for only majority,
No, it's
odd
just,
and even
it's
may
not that,
work.
we're not saying that it won't work. I'm just saying you're going to have a better experience because you will be able to predict more easily your failure scenarios. It's not something like GFS where, you must run some odd number or else you can run into problems. It's definitely more I put that up there as an operation tip because it's not immediately apparent. And I deal with, or I work with folks on a regular basis who have the most off-the-wall network configs where they want to have 1 node in Oregon, 1 node in Japan, 1 node in Ireland, and 1 node in Dulles, and link them all together. And it's like, well, you only have 4 nodes in that case, and they're all split really far apart, and you're sitting here saying that the performance of it is unacceptable. That was assumed. There's only so much we can do here, so. Yes?
The FTP has dynamic membership. Can you add and subtract?
Yes, you can. As far as removing, so actually that's one thing that I'll show you. You can also dynamically change the overall configuration because the configuration for etcd is stored in etcd. So, and yes, your question.
Is there a good way to do, say, hierarchical clusters? So just say you've got one bunch of nodes in the US West and one in the US East.
Mhm.
Do they each run their own little forum and then like 2-node supercluster?
So, yes, they should run their own individual clusters. We are working on a federation mechanism so that you can have a central spot that you query that then federates out to other clusters as well by key space. We're also working on something where you can specify delayed replication or like a kind of delayed sync where it's not directly a member for consensus purposes, but it will replicate values from one cluster across to another. Specifically, that's for the what I call the oh shit case of somebody deletes a value and it's not as bad as you would necessarily think, but because of that write write-ahead log and the fact that everything is indexed, nothing is directly deleted from etcd because you can always rewind the index and just see what was there, kind of like a git log. But it allows you that panic button to not have to go back and find what an index was when something was deleted. Like, this values don't get replicated from cluster A to cluster B until 600 seconds have passed. And so it gives you like kind of a definite delayed mechanism where everything is getting over there, but you also know that if something really crazy goes awry, or you lose all of the nodes in a cluster or something, that everything's still safe. That being said, also, like I said, etcd writes that write-ahead log to disk. I have folks that really, really want to run etcd without a disk in the machine and run it on a RAM disk. That's great. The performance is wonderful. If your entire node or your entire cluster shuts off, your data is gone and there's no way to recover it. So just keep in mind it's on disk. And I realize that some of you are going, well, duh. I mentioned this because it wasn't immediately apparent to some people, so I figured it's better to err on the side of being explicit. So, okay. Now, let's get into actually doing some fun stuff with this cluster of machines. So, what I'm going to do first off is I'm going to look at my instances here, and I see that I have, first we'll just say Redbeard, and I'm going to say give me less space. There we go. So, go ahead and grab an IP address, and we'll say, probably turns that I can actually see it, SSH core at that. Actually, I want to forward my agent. So I say yes, let's go ahead and log in. And that is impossible to read, so let's change that a little bit. Okay, so we have a cluster of machines. Because we are on EC2, I can look at what it actually fed it via the metadata. So I can say curl HTTP 169.254.169.254/latest/user-data, I believe. Yes. So it passed in. So configuration of all CoreOS hosts happens via cloud config. For anyone who's worked with kind of Ubuntu cloud images or some of the like OpenStack various flavors, cloud config is a mechanism for providing a manifest to a host that defines the things that should happen when that host comes online. Cloud config was originally written in Python. It was originally written by Ubuntu. It was later adopted by Red Hat and most of the other major distros. It's what has allowed Amazon to be able to configure a lot of their stuff. In addition, though, so before coming to CoreOS, I think I mentioned this before, I worked for many, many years at Red Hat. And I remember as soon as folks started rolling things out on OpenStack, they said, so I've got Kickstart and I want to use Kickstart. Well, sorry, you can't use Kickstart on a cloud image. You have to use cloud config. And it gets into this diverging path of, well, if I want to deploy things in mechanism A, I have to use this process, and if I want to deploy things in mechanism B, I have to use this other process, and there's no easy way to merge them. So when I started at CoreOS, I kind of stood on the table and jumped up and down and screamed, saying we have to have one unified thing. I personally don't like cloud config, but it's an easy standard to work with. You know that cloud config file is going to work on OpenStack and on EC2 and on DigitalOcean and on Pixie, because we even devised a mechanism where you can provide that cloud config file as a kernel command line option, and cloud config itself will read it in and process it even if it was provided on proc command line. That's another one. For anyone who didn't know, proc command line gives you the actual options that were fed to the kernel when the machine was booted. So just a little bit of trivia there. So if this was a physical machine that was booted via Pixie or anything else, we would see all the stuff that was actually handed to it. But back to what we've got here. So our cloud config file has a CoreOS section. That means that everything under that namespace only makes sense to CoreOS. If you try to do it on an Ubuntu image, obviously it's not going to work. We went through and we specified that there were a couple of default systemd units that were shipped that we wanted started. We wanted to start etcd and we wanted to start Fleet. Fleet is an orchestration tool that we built that uses etcd. So if I say fleetctl, actually make it a little bigger so folks can see. If I say fleetctl list machines, it tells me I have 3 machines in the cluster and shows me where they actually are. Now, the way that it's actually doing this on the back end is that it uses etcd, as I said, to store everything. So if I were to say etcd-ctl list, shows me I have this CoreOS. And if I throw recursive onto my list, recursive, I see, oh, well, this is not any of the Fleet stuff, but it is telling me about the reboot lock. We'll get to that. But if I were to use this hidden namespace, which you know it's hidden because there's an underscore at the front of it, we see that there is a Fleet key. If we do that, we see that there's information on each one of the machines in the cluster, including who the current engine leader is. If we wanted to look at one of the actual keys, we can say etcd-ctl get instead of ls, and we see we get a JSON structure back telling me what its IP address was, any metadata that was attached to the cluster, which reflects that there's no metadata there. So this is how we can kind of discover everything there. Working with etcd is as simple as etcd-ctl set foo var. That's it. It's now there. If I were to get that, the data is definitely there. And if I were to say that I wanted to see the extended version of that, we'll actually get some of the headers back. So I can see that the current etcd index is set to 1188. It's a monotonically increasing number, telling you how many different index periods that's gone through. I can also, when I do my set, TTL equals 5. Actually, forget whether it's before or after. Yeah. TTL 5. Foo baz. Now if I do that get, we can see the TTL counting down there. TTL2, TTL1, and then it reads the key. So if you've got data that you want to write to your cluster that is as of a specific point in time, or that expires itself, it's something that's relatively easy to do. Now, everything that I'm doing here with etcd-ctl, you can use any of the libraries for. You can do it with raw curl calls. In fact, let me go ahead and set this key back. Come on. So when I go to do my get, you know, we've got the extended there. I can force a consistent or a sorted view, but I can also do something where we end up watching various other keys. So let me get logged into a second host here so that we can get more into the realm of actually doing useful stuff. And this is going to be very easy. Or get forward my agent or add that. So we now have 16.127 and 12.132. And I say etcd-ctl get foo. It's currently set to bar. So what I can also say is watch foo. So in other words, just hang out, just watch it. Let me know if anything happens. And when I set that to baz, it immediately responds and releases the key and tells me what the data changed to. So now you can program things easily in such a way where you react to when configuration changes actually occur. That's, yes?
So when you delete all these, I just do public.
No. I'm talking to my actual host. So what's actually happening on the back-end side here is this host is listening on 4001 for any client requests, and by default, etcdctl makes requests to 127.0.0.1:4000. So no matter what host I'm on, it looks to talk to itself and it reads its local values, but if I go to write it, it redirects it to the leader. So being a little bit more explicit about this, if I were to say http://127.0.0.1:4001/v2 for the API version /keys /foo, I see the entire action and everything come back, because this is the raw call that tells me everything, including the index, so that I know when I wrote that key as of when it's there. Whereas etcdctl is just it's hiding some of that from you so that it's more easy to use in like bash scripts and stuff like that. So another one that I want to do here is I'm going to do a different watch that's called an exec watch. And in this case, I'm going to say, hey, go ahead and watch that key foo, but what I want you to do is run the command echo the value of foo has changed. And now it just hangs out waiting. When you saw this dump back a bunch of extra lines before, that's just because I hit enter a bunch of times to make it so that folks can see things a little easier. If I go over here and say set back to bar, it tells me it's changed. It actually ran this script, echo, to react to the change of the key. And I can sit here and keep changing the key, and it will keep reacting to it. The idea there is that you could, when your application comes online, you could say, who is my database? And if there is no value for that, it can just hang out and wait until some value is set. And then as soon as the database actually comes online, it publishes itself to the master, your application immediately knows, and it can start doing reads, or writes in that case. That's what I meant by, it becomes this locking service. So you use this to take a lock or to find who the master or to find who the components of your application are, because in this case, I'm talking to 127.0.0.1. If you're ever in a boat where 127.0.0.1 is not available, again, we're back to that picture of sandals. I can't really help you. When localhost is not online, there may be bigger issues at hand. Now, let's say that I'm doing this command, this exec watch command, and I want to get a little more information. Well, let's start out with doing the get. And what I'm going to do is I'm just going to throw in debug. And one of the things that we tried to provide is an actual example of the command that you can run from curl so that you don't need to use etcdctl. We're really trying to make it as simple as possible. I've never done this on exec watch, so maybe it will faceplant. Okay, so we had a wait equals true in this case. So for this, I can run curl wait equals true and echo the value changed. And echo the value changed. We hang out, we wait a little bit. Set that back to bar, and I run this here. I can see the old index and the new one, and we can keep on responding to that. Still making sense for folks?
A couple of questions, if you don't mind.
Yes.
What kind of are these connections persistent? Are they TCP/IP connections?
Yeah, it's a TCP. It's basically a long pole happening in the background, so it will hold itself open.
Okay. And what kind of network traffic is going on between those nodes?
So on the back-end side, there's a heartbeat that's happening every n interval. So Amazon is a little bit slower than some of the other cloud providers. So in each of the different what we call OEMs, so that would be Pixie or Amazon or Rackspace or GCE, we actually use Cloud Config to make some changes specific to that host. And those are always going to be, if they are there, because not all of the various providers or various OEMs need any changes, they're going to be in a specific partition called user share OEM. And the only things that are there are things that need to get tweaked for that host. So in this case, you can see I've got this cloud config, and the only thing that this cloud config is actually doing is going through, retrieving any metadata from EC2, and we're setting the peer election timeout a little bit longer, just because Amazon, like I said, has some issues on the speed front. But what I can also do there, let's say that I wanted to make modifications to the actual startup script for etcd. I mentioned that that was done via what's called a systemd unit. So systemd units are going to be services. They're also going to be devices. So,
Sorry, before you go off.
Yes.
Continuing on that network question.
Yes.
When you scale to, let's say, 1,000 nodes,
Uh-huh.
those TCP/IP connections between all those 1,000 nodes,
Mhm.
you can imagine how many connections, permutations, combinations are.
Yes.
How many nodes have you tested to see how it scales?
We have tested up to etcd clusters of 500 nodes.
Okay.
That being said, we never have more than 9 actively participating in consensus. So it's kind of a proxy mode where etcd is running on the host, but it's not even guaranteeing that wall file isn't being replicated to all of them. So really, it knows about the core cluster of machines and can redirect that read over to something that has that, or redirect the write over to the leader to guarantee that the file is actually being, or that the change is actually being done in a sane location.
I'm not even worried about reads and writes.
Mhm.
Let's say there's no activity. There is still activity because of the TCP/IP
Well, so
connections.
yes, so 2 things there. One, only the nodes participating in consensus are participating in the gossip protocol.
Okay.
So that's one of the reasons why we limit it at 9 nodes. One, because, like I was saying earlier, if you've got more than 5 nodes failing in a single location, you've got bigger issues at hand. But 2, when you have even 9 nodes participating in consensus, there's a lot of traffic going on.
Right.
So by minimizing that down a little bit to 5 nodes, you are scaling down the amount of gossip traffic, and you're saving more of the actual TCP connections available in the kernel without doing additional tuning to make sure that everything's going to be performant.
Well,
Now,
so let's say that's the case,
Mhm.
but let's take the example you gave earlier where a bunch of nodes are waiting on a service to come up, like
Mhm.
a database.
Yep.
Let's say I have a cluster of 1,000 nodes. I have these 500 nodes that depend on a proxy service to come up.
Mhm.
Right? They're persistently listening, and so there is constant traffic going on, right? So I'm assuming even from members. So there's one thing about membership,
Mhm.
and there's the other thing about well, I don't know how you propagate the topology to everybody. I'm guessing these 9 guys will somehow notify when the topology change. Like if a node goes down, how do you notify?
I think maybe you're confusing watching with polling,
yeah,
because you can register a watch and there's no traffic until something happens.
exactly.
Well, actually, I'm talking about.
Yeah, the
so
connection is held open, but you're not actually passing data on it.
So typically, when you reach a certain limit, TCP/IP just by itself becomes extremely chatty,
Mhm.
right? When you talk about 1,000 nodes, you imagine if you're connecting to each other node for topology changes or for I don't know. Again, I don't. That also depends on
Yeah.
how you do distribution of keys. Are the keys all meant are handled by one node? I mean, I'm guessing you have some distribution of keys across the board.
Yeah, so the key distribution all happens via RAF protocol.
Okay, so
So-
I'm guessing if there are 1,000 nodes, each one of them has a certain range of keys it maintains.
No, they do not. Each machine has the entire write-ahead log on it,
Mhm.
and only the machines participating in consensus have that log on it.
I see.
So it's something where any changes happen via the gossip protocol, but each machine has the entire log on it. So each machine should be able to service reads each machine participating in consensus will have that entire write-ahead log and should be able to read from it at any point in time, up to when a snapshot was taken, and assuming that data hasn't been purged from that before the snapshot.
Okay.
Because the snapshotting occurs so that you can actually go through and like reap really old values and save space and have a checkpoint at time that you're able to recover from.
Okay. Anyway, I don't want to hijack the time, so
Not a problem.
We can probably follow up later.
Okay, yeah.
Thank you.
Do you actually set a hardware version that you design on TCP?
The heartbeat messages are sent via TCP, but the heartbeats also contain any of the values that need to change in the entire cluster. So when we send out those 50 millisecond heartbeats, we're sending out changes to the keys at the same time.
And
If there are no changes, yes, we still send heartbeats. Yes, we do. Because the heartbeats are actually used for the election and for election timeouts. So, yes.
What is the read in the node which is not part of the forum? What is it? It looks like only the nodes in the forum you can get it.
So a read from a node that has lost quorum will only be up to its committed index. But
There's no change. If everybody is up, there's no service that let's say it's a 9-node cluster, 5 are part of it, and the other 4 are not.
yep.
And if a read comes to one of those 4 nodes,
Mm-hmm.
does it need to get redirected or is it node that's
So if the nodes are not online, I believe the response is that. Okay, so if we've lost quorum.
they were never part of it.
Yeah, I think the question is that
standby nodes, they're not.
Oh, yes. If you do a read to a standby node, it gets redirected to someone who's participating in the consensus.
Is it chosen randomly or
Yes.
is it-
Well, if it's a read, yes, it will be chosen randomly. If it's a write, it gets redirected to the leader.
So in other words, you've actually got sort of 3 flavors of force. You got a master, you got a few in the consensus, and then you got
There's actually a few more than that because there's also one called a candidate. The candidate is someone who is participating in the election but has not been elected the leader. This is all stuff that's actually covered in the RAF paper, yeah. And that's because in Paxos they set like 9 different states or something to that effect, and the whole idea was also to minimize the number of operational states. So one of the things that they do is in the case of the, let's see, do I still have RAF consensus up? Yes, I do. So you'll notice here, as these timeouts happen, it randomizes the timeouts between 2 intervals. It's suggested to set them between 150 and 300 milliseconds. I think. Yeah, it's between 2 values. And the randomization just guarantees that you never have 2 machines converge at the same time, or that everything converges correctly, because you notice each time a heartbeat goes out, it resets the randomized timer. So in some cases like that one, it was less than, or it was beyond half, so it didn't like drag the timer even further forward. Let's see. Match index. So everything's paused right now. Zoom. Come on. Resume. Apparently I crashed it, so.
But so, in any case, so the claim is that irrespective of the size of the consensus, you can scale to 1,000, 10,000.
So there are definitely limits because again, that's the idea of kind of the proxy type workload there. We have, so that's where I say we've tested it with 500 nodes participating in that, but again, there's only 5 nodes participating in the actual consensus. There's only 5 nodes in that gossip protocol actually sharing the wall file between them. Everything else just redirects over to those, but is listening on the same 127.0.0.1:4001 to make sure that you just have a known spot that you can always query that should get you to the right location. So that way you don't have to do a DNS query to figure out who to talk to before you try to talk. You know that you can just start from there. Yes?
So the other nodes can receive notification something is updated.
Mhm.
Slaves can be notified if they chose to or
Yes, they can.
they can.
Yeah. That's the difference between just reading a value or doing the watch on it and waiting to see. There is also the ability to, like an atomic compare and swap, to make sure that data is only changed if it needs to be.
Because the watch I understand is that he has a watch for specific key. Because if I don't know which
So-
key maybe.
No, I don't think that there's like a recursive watch for a specific key space.
If I 100 values, if I need to know any one of them change, I need to have 100 watch.
Yes, and that's what the libraries are for, so that you can. That's as polite as I can say. The kind of open source version of PRs. PRs are wonderful. Patches are accepted, but also if you have questions about that, I will say I'm not a developer. Like, I am definitely an operations person. I've been a sysadmin for 16 years now. I don't try to argue the consensus side. I can tell you that if you go into our CoreOS on Freenode, Xiang and Yichen are the two main guys working on the consensus protocol side of things, and then also, and like their major goal is to guarantee that the consensus is correct, like more than performance right now, because they want to have a very, very strong guarantee that you can trust the actual data that's there. We have a few other folks, BC Walden and John Boole, who are working on the performance side of that as well, to guarantee that we can get up to a really ridiculously high number of nodes, ideally participating in consensus if possible.
Excuse me.
Yes.
If you say that only certain number of nodes are participating in the gossip protocol,
Yes.
heartbeat is only between them, right?
Yes, exactly.
So if any other node crashes, how do they know about the crash for higher HA purposes?
If another node that was not participating in the gossip protocol,
Exactly.
it's irrelevant to the gossip protocol.
Not for the gossip protocol, for HA of the whole cluster, right? I have 100 nodes, 5 nodes are in the quorum, right?
Yep.
So if one of the other 95 nodes crashes, I may want to recover that or probably move that application to somewhere else, right?
Okay, and that's a great time. That's a great time for us to start talking about something else that we can. So, wait with me. I will show you how we can handle some of this stuff. Also, okay. So, you briefly mentioned or saw me mention Fleet CTL. Damn, it's already 8. Okay, so Fleet CTL list machines. Fleet is a mechanism for sending a systemd unit to a group of machines and operating on it. So, what I mean by that is, in this case, we have systemctl cat, we'll say etcd.service. So this is a systemd unit file. We have a little bit of preamble that just has a description, and then we have 3 files that are actually composed together to provide that entire configuration. You see that these two are actually just providing environment variables, because we designed etcd so that most of the configuration could be provided by environment variables if that's the way that you wanted to run it. And that makes it really easy to do inside of a Docker container if, again, that's how you roll. So what we have here is setting our peer election timeout. We actually have our discovery location, what we are advertising ourselves as, and so what we're going to do here is, now that we've seen the basics of what a systemd unit looks like, we're going to write an idiotically simple systemd unit. So we're going to say hello1.service. So again, first we need a little bit of preamble, so we're going to say description equals my hello service. And then we're going to say, for our service section, exec start equals bin echo hello world. Okay, that's a complete systemd unit. If that's as simple as you want it to go, that could run as a complete systemd unit. Now, one of the things that systemd actually does is it provides you semantics similar to Monet or daemon tools, so that you know how a process is actually supposed to run. In this case, my process is going to do something in the foreground and hang out there and wait. In other words, its type is what we would call a one-shot. Systemd understands a process that's going to be long-running and in the foreground, and if for some reason that process stops running, it should restart it and make sure that it's fully online. It also understands a process that forks or a process that double forks. It knows how to actually handle all of these and handle some of the performance resource limitation of each of those. So if I were to take this and say, copy this hello1.service, which will need to happen via sudo, into etc systemd system, that service file is now installed. And if I were to say systemctl status hello1.service, we see that it's loaded. It has never been started. It's sitting in an inactive state. And we see the path of where that service is actually located. So again, if I say systemctl stat cat hello.service, there's my service. So let's go ahead and actually start it. I start it, and it's hanging out in the background. We see that as a part of its status, it ran once, it exited. Because it exited with a 0 error code and it was a one-shot, it knows everything is okay. And we see that it captured everything into its log. Now, if I were to say journalctl -f as a part of this, so here is the error message in the log. You know, this is the equivalent of varlog messages on an entire system. But one of the things that systemd does that really gets the goat of a lot of individuals is that it stores all of this in a binary format. That means that you can't just do a tail on it. But what that does mean is that if you only want to see your unit, if you only want to see the things for hello1.service, you can do that. You can say, just give me the data on my service. Or, if you want to send this off to something else, you can get it in a machine parsable format. So each one of your log messages is now available in JSON. That means that you can easily take your log messages and stream them off to something like Logstash, where you ingest them and can make sense of it. I don't know if anyone here works for Splunk. If you do, I apologize, because Logstash is eventually going to eat the lunch of Splunk because of that whole, they're not charging you an arm and a leg for it. Splunk is awesome until you hit that 501 megabytes a day and you see the price tag come in and need to go change your pants. So, having something where your logging system can just emit the messages in a machine streamable format or a machine parsable format is great. You know, if we were to go one step further with building a more complex service, let's say log exporter or log export.service. What that would actually look like, and I'm not claiming that this is a good method, I'm just saying that this is something that you could do out of the gate to just get things running. I could say unit description equals log exporter. Now, why am I doing this right now? I'm doing this to show you an easy mechanism for how systemd units are built. Systemd units are very, very easy to make. That's the big takeaway here. So my service is going to be exec start. Now, because systemd does not handle it treats pipes as delimiters. So in this case, because I want to run user bin journalctl -u hello1.service pipe through ncat etc. to my log host, my log stash host.tld on port 3000. That would now actually stream all of the log messages over TCP. The nice thing about ncat, which is written by Fyodor, the creator of Nmap, is that it supports TLS and a lot of other things directly. So you can easily guarantee that your messages are not getting lost and that they are secure over the wire, etc. Use SCTP instead. So, but again, takeaway. Systemd units are simple. So now that we know how to write a systemd unit, let's actually look at what it takes to guarantee that that is running in a cluster. So what we're going to do, we're going to make this a little more complex. I'm going to go from saying hello world to bin sleep. So my thing is going to run for 60 seconds and exit. And if I were to say fleetctl start hello1.service, it goes through, and it should be running a little bit faster, but it schedules it out to a cluster. And now when I say fleetctl list units, it tells me that I have hello1.service, which has been scheduled out coincidentally to this machine. Because I already had a hello1 service, it had a little bit of a freak out, so let's do sudo rm etc system, actually, yeah, it's fine. Fleetctl status hello1.service. Yeah, so it actually just fired up that one. So let's do sudo rm etsy systemd system. Come on. Hello 1.service. And we're going to say system, we're going to basically tell it to reread all of the systemd units. So systemctl daemon reload. And now we're going to say, hey, start that again. So when I go through and I show my status, it really isn't nice. So let's do this. Let's say t hello 2, 3, 4 from hello 1.service. Now we have a bunch of hello services. So let's go ahead and start all of them. And we go through, and hello 2, 3, and 4 went ahead and got launched. I say fleetctl list units. They're all doing their thing. These are in the process of activating. Additionally, I can say fleetctl journal hello 2.service, which is running on a different host, and you'll notice it actually goes out and talks to that host. I don't need to find out and do a lookup and SSH over to that host to actually look at the logs. Fleet will handle moving over to the host using the fact that I tunneled in and forwarded my agent and actually go across to the host, log in, and retrieve everything. So we see that these are in a started state, and momentarily they'll stop. Now, where these are actually being stored, and this is what happens when thousands of machines are actually running and scheduling things out into the cluster. How do you know when a service goes down? Even if it's on a machine that's not participating in consensus, that's because when you submit a job via Fleet, Fleet is monitoring the state of that job on the host where it's actually running and notifying everything that's watching in etcd. So in etcd-ctl, we mentioned before that all of the information for Fleet was stored in this key. So I'm going to say, hey, show me everything in that key, and we see that all of the information about the actual job state, the target state, and then the content of the job itself are all stored there. Yes?
I can actually, instead of sending systemd commands to Fleet, I can just send it to etcd.
Yes, you could. And in fact, so one of the things is fleetctl actually talks directly to etcd and writes all of those values in. Now, that being said, we're in the I think now we have an HTTP API exposed for Fleet. And basically what happens is it is exposed as a socket on the system, and then you can take that socket and use a systemd socket unit to expose it out to the network. So like I said, there's lots of different types of units. So let's talk about this here for a second. Systemctl status docker.service. So Docker's not running. Yet when I do a Docker PS, it's there. If I do a Docker images, everything's there. If I do a Docker pull busybox, it kind of goes off and starts retrieving everything. So what's the deal here? I say systemctl status Docker service, and it's not doing anything. And yet without... Oh, there's a whole lot of stuff going on with the busybox right now. And yet, if I do a systemctl... Oh, wait, it's running. What's going on there? The reason is for folks who have been around back in the day, there used to be this thing called socket activation. And socket activation, the reason for it was because you had a lot of services that you wanted to run, and your system only had 128 megs of RAM. So how do you run FTP and a dozen HTTP processes and everything else? That was through socket activation. But the problem was that socket activation itself wasn't terribly efficient. It was just a method for oversubscribing the system. Well, one of the things that happened with systemd is they found methods for making socket activation efficient. So you see that I have status Docker service. If I do Docker socket, we actually start the Docker socket for listening to those API requests out of band of when the service actually comes online, in the same way that we do with, for example, sshd.socket, where the SSHD socket listens on port 22 and then spawns an SSHD process when the individual actually logs in.
Is it like NAD kind of thing?
Yes. It's like a better version of XINetD or INetD. Yeah. That's exactly what's happening there. And, you know, we've got this. So we tell it, this is the Docker socket. And this, or the SSHD socket. And this gets into the next very important point. So we say the port that we want to listen on. And you'll notice there is this target. Remember, we talked about the coordination targets earlier of sockets. So this allows us to bring the sockets online immediately, as soon as that box is booted, so that we can start listening for connections just in case. And the kernel will buffer those connections until it can actually bring the additional processes online to then service the connections. So that allows us to really make sure that if anybody needed a response, we can start reacting to it as quickly as possible. Make sense? Okay, so we've gone over a lot of stuff with systemd, and now we've got Docker. So let's go through and talk about our hello container here. So I've got this hello 2.service. What would it look like if I actually wanted to run this as a Docker container? Well, I go through and I say user bin Docker run. Now, you notice I put --rm on there. So we established we've got folks who are familiar with Docker. I don't want to run things in the background there. I don't want to detach. I want to run things in the foreground, because systemd knows how to run things in the foreground. And anything that gets sent to standard out or standard error will automatically get logged, so you don't need to figure out how to do some logging mechanism. So I do --rm to make sure that it cleans up after itself when it leaves. Because again, the idea of this container is to be something ephemeral. It's a job that runs and goes away. And if there's configuration that needs to be handed to it, you hand that in addition as a part of the runtime. That way I can take my container that I built on my laptop that has my application and has a SHA-1 sum attached to it, and when I hand it over to somebody to run in production or in staging, they can verify that SHA-1 sum, they can hand it the configuration that makes sense for staging. Maybe it's talking to SQLite, maybe it's spinning up 5 copies. And then when it goes on to QA, they can hand it the configuration that makes sense in QA, and yet that SHA-1 is the same. So I know that my code hasn't changed. Or conversely, the sysadmin can go, dude, I have not modified anything. You can verify that I have not modified anything, and if the code isn't running, it's your fault. It's either the configuration or it's your fault. Look at the configuration. Is that cool? Okay, go back to point number 1. Fix your code. So that's why you don't generally want to embed configuration files into a container, because then that way you can be guaranteed that that one container will run the same at every stage of the lifecycle. You can now start to do application lifecycle management utilizing the container in a more efficient fashion.
So for every container, do you have to create a different unit, or can you launch multiple instances of the same unit? Same service?
So you can. Those are called template units.
Okay.
And I'll show you. That's probably one of the last things that we'll do, just because it's useful, but there's more important things to see. So, to take this, I can now say docker run rm. Hey, fire up busybox, and run bin sleep 60. That's it. If I just have a simple command process that needs to be run, that's all I have to do. And this is a useful systemd unit that now just will spin up a bunch of namespaces inside of Docker to then actually fire things off. Now, I also mentioned that there's a different type of container as well, called a systemd nspawn container. One of the things that we do is, so if I'm just going to go ahead and say docker run -t or -t-i -rm busybox bin ash. So here I'm inside of this container. I'm going to say sleep And I'll say 3600, so it's just going to hang out and do that. And I'm going to hypothetically, oh, there we go. So I'm detached from that container. I do a docker ps. I see that it's actually up and running. I do a ps faux www grep sleep. I see from the host, I can actually see that sleep command running, despite it being inside of a container. And yet, if I go through and I spawn up another container doing the same thing, and I do ps, I don't see any of the stuff. I don't see the other container. That's the point of the namespaces. But as far as the namespaces go, so now I have these containers, they're doing different things, they're running in the background. Let's say I need to actually troubleshoot something that's going on with them. Well, there's two things that can happen. One, you can do a docker attach, and if I connect to OF5, oh, that was my newer one. Let me get back out of that one, because I wanted to connect to the one that was doing the sleep command, 60C. Well, I'm running that command in the foreground, so sleep is still doing its thing. So what I actually need to do in that case is I need to enter the namespaces for that container. So what we can do is I can say docker inspect, and by the way, the 60C that I was running there, that's just the first couple characters enough to be unique about that container. That's how I got it. I could have also given it the name of the container, but I cheated. So I say docker inspect, and this is just another way of guaranteeing that I know the exact PID that is the beginning of that container. So I've got that PID namespace, so I can say nsenter. I want to enter the target PID of 1035, and I only want to enter the PID namespace. Now I do that, and when I do, I enter the wrong one. PID, oh yeah, PID and mount namespace. Bin hash. So now you can see I'm inside of this container. When I do my PS, I can see that the sleep command is there. I can't see anything that's happening anywhere else. And if I run an ifconfig, I see all the networking on the host. The reason for that is because when I ran my nsenter, my namespace enter command, I did not tell it I wanted to enter the network namespace of that process. If I run that and specify -n to enter the network namespace, and I go back and I do the same things, my process looks the same, and yet when I run ifconfig, I don't see all of the namespaces from the host. That allows me a troubleshooting mechanism to get into a container to actually figure out what's going on inside of it without affecting its actual running state. So, we've started talking about selectively getting into the namespaces of a container. Let's say,
Brian.
yes.
So this, how is this unique to CoreOS? Some of these
This is
versions
not.
are- okay.
This is
No,
not.
so it's
I'm
still
making
not-
sure that,
okay.
you know, so where this starts to get unique to CoreOS is if I've got this process, and let's say that this is an actual TCP listening process. It's Apache or it's some FTP program, and I need to actually see what's going on with the networking on it. Well, it's not like you can just run TCP dump. Because again, if I were to take a look at our user partition, it is mounted read-only. We cannot affect that. So I've got two options. I can either start sucking down binaries onto the host, or I can spin up what we call a toolbox, which will pull down a Fedora runtime and spawn a systemd nspawn container, and then it will actually mount the entire host into that container. We're doing a lot of inception there. We're getting into dreams within dreams here. So, okay, do that. So one thing I will say, my email address, again, is brian.harrington@coreos.com. So if you have questions, feel free to email me. So, you're lost. I am here to answer your questions.
the way my daughter feels about unicorns.
Okay.
This is really beautiful.
Okay, so the what?
I'm really lost. Repeat what you said so that
Okay, so
process it slowly.
what we have got going on here. So while that's happening in the background, I'm just going to switch to this other machine. So like I was saying, we have this with this command called toolbox. This is one of those things that, again, wows people. It's really not impressive, especially once you see the man behind the curtain. It's a shell script. And it's a shell script that does a bunch of stuff of going through and, defaulting to Fedora and then reading out values from your home directory to see if it should override any of those. But then what it does is it goes through, it does a Docker pull. So we're cheating here. We're some parasite that's actually just relying on the fact that the Red Hat guys push a Fedora container up and they maintain it on the Docker hub. And then we pull it down, we do a Docker export and immediately untar it to the file system. We get rid of the Docker container because we're done with it. And then we run this systemd nspawn command where we bind mount user into media root user, and we bind mount / into media root inside of this container. And we do everything as this other user. And the result is now I'm sitting inside of this container. And if I say cat etc os release, it tells me I'm running Fedora 20. And if I do a yum install -y install TCP dump, well, I've got a full package manager available to me inside of this container, so I can go through and I can start pulling down any troubleshooting tools I might need. So now I can actually go in and I can run TCP dump from this portion. I'm actually just going to cancel that real fast because, again, we talked about these things. If I run ifconfig, I forget. No. So if I were to, let me see, Control P.
So there's a container with the parent or the host namespace.
Yes, it is a container that is running in a majority of the host's namespaces.
Is it like some security breach?
So yes and no.
Well,
Yes and no.
if you have root on the host,
Yeah. Yeah, exactly. I ran this as root, so.
If you can run a container that can take control
So-
of the.
So this is actually a good segue. Who here thinks containers are a security mechanism? I'm glad no one raised their hands. Namespaces are a security mechanism. Containers are just a trick of light and shadow that use namespaces to then do these fancy things. If you are relying on containers as a security mechanism directly, keep in mind so let's
When I'm running something from Docker Hub, potentially
yes, you are running arbitrary code on your system and trusting it.
someone can run this, and all of a sudden it can take control of my other containers in that host.
Yeah. So, what I wanted to find here.
But Docker already wraps everything in namespaces, right? The lib container.
but what's it being
No,
hosted
they
on?
don't.
Like you could.
They don't. So, Docker must run as root right now. There is an actual if-then statement in the Docker code where if you are attempting to run Docker-D as non-root, it goes, whoa, you can't do that. You got to run me as root. But the thing is, if Docker-D is running as root, and it's not carving out user namespaces, because user namespaces have not been implemented in Go yet, which Docker is written in, any container in which you have root in the kernel. Do not treat Docker containers as a security mechanism. That's not something like, so the Red Hat solution to this right now is, SE Linux will fix it, which I trust Dan Walsh. Dan Walsh is a really smart guy. I've worked with him a bunch. He is the one guy at Red Hat who truly understands everything about SE Linux. So what he did was he took the idea of SVirt, which is used for protecting hypervisors, and slapped it onto Docker. Okay? I still want my user namespaces. So we're working, specifically Kelsey Hightower and Brandon Phillips from the CoreOS team are working with folks over at Google on really pushing through the user namespaces, which will then make everybody who uses Docker happy. That will be various degrees of happy, because if you're not using a kernel new enough to implement user namespaces, rel 6, that will not do you any good. This is one of the things where running a new kernel really behooves you. But, so I've got this, I should have been actually installing my TCP dump in the background. But so you've got this container. It's going through, we can install any tools that we might need to do diagnostics or troubleshooting on the host. We can selectively enter or leave namespaces as needed. Which means then from inside of this container, I can do a TCP dump, or even something where I listen in SSHD on this container on port 22 and move the CoreOS SSHD over to port 2200. And now if I SSH to the host, I'm actually inside of this container. And one of the differences that you will see there is that Docker wants to be the init system inside of the container. If you are running Docker, it expects whatever process you start to be PID1. The difference with a systemd nspawn container is it has all of systemd. It has a full-fledged init system inside of it. So you don't have to play games with things like supervisor D and like, well, Docker doesn't want an init system, but then somebody wrote a kind of init system for it and shoved it in and did all of that. And, I can say TCP dump -vvv port 22. And we see all of my SSH traffic in a kind of a loop here where it's actually doing things. Or I can say, show me port 4001 because I want to see things going on with etcd. And I go through to, let's see, this is a, so there is some of the heartbeat traffic actually going back and forth. So now you're in a boat where even inside of a container, you can affect the host. To really drive this home, you can do basically anything inside of a container. One of the customers that I've been working with extensively runs the HP Smart Array tools inside of a container to affect the JBOD for the Smart Array controller on the host because they run it in just HBA mode. It's not like HP is really hot to trot on shipping all of their tools in every specific format, so they kind of do it in a CentOS compatible one, but they don't really want to then fork off and ship them for everybody. But you can actually spin up these containers to affect things on the host. Now, that being said, let's go back to Docker. Let's say Docker PS. Let's go through and say Docker attach F5. Oop, helps if I spell attach right. So now I'm back inside this container. And if I try to do a mount-o remount on that, you get permission denied. That's something that should normally work. It asks if I'm root. Oh. You tell me, am I root? Yes, I'm root. Why did it give me permission denied? That is because, since about 2002, root isn't what you think it is. In the same way that these containers are a composure of namespaces, root is a composure of capabilities. Which is to say, if I go over to my laptop here, where I have full everything, and I say man capabilities, it starts going into talking about how root is actually combining things like cap audit write, cap fowner, cap kill, cap net admin, cap net raw. The reason for this is because, let's use ping as an example. You want to ping another host. That requires sending out an ICMP echo request, opening up a raw connection, and waiting for that ICMP echo request to respond, that ICMP echo reply. It used to be that that required root on the host. So the solution for allowing non-root users to ping things was to make the ping program set UID root, which is horrible. Because now as an attacker, if I can replace that binary with my own file, I can get you to run arbitrary code just by running the ping command. So what they did was they broke down root into the series of capabilities so that things like capnet admin or capnet raw allow you to selectively have those type of root capabilities without giving you the whole thing. And what Docker does for part of its security mechanism is on top of namespaces, they drop all capabilities and then they start layering back on the ones that you need. That's the difference between a privileged container and a non-privileged container. The privileged container does not strip away any capabilities. So, if I were to go through and take this container right here, and I were to go through and do a docker run, oh, I just found it, docker run, but I throw in privileged. Now, when I do mount-o remount, it works. I don't get an error. That's because the cap sysadmin capability, which is what's needed to do a mount, is provided into it. So this gets into things where, like, I've taken Gluster, I've run Gluster inside of a container, but a privileged container, mounted a physical disk from the underlying host into that container, did my makefs on it, did my actual install of it to Gluster, then presented that Gluster file system back out to the host so that now the Gluster file system is shared with a number of containers that can then selectively use it. And now Gluster is handling the transport of replicating any files that were written across to all of the hosts. Again, anything that you can do on a regular Linux system, you can do inside of a container. Now I say that, and that's a lot like, high school physics. It's a lie that I tell you to make it understandable so that you actually try these things, and there are edge cases to that. But yes, Ram. Networking?
Yeah. What about networking between hosts?
Oh yeah, so that's one where if I were to go ahead and run this again, and I say -net host, I think. Where is it? Net bridge. Docker bridge. Net. Yeah. --net equals host. Oh, net equals host. Now, you see, I'm bridged all the way out to that there inside of a Docker container. And what that command did was similar to when I did the nsenter, but I said don't create your own network namespace. This created an entire container without. Now the entire container is sitting on the host's network namespace. So, I'm gonna do this real fast. So, two things that you need to see, because I promised them to everybody, and I would be remiss if I did not. So, if you go to buildroot.org, Buildroot is a tool that's used by projects like OpenWRT and Yocto to build embedded Linux systems. Doesn't sound especially interesting, but this is where some of the magic comes in. So if I were to go in and download Buildroot, which I've already done, and I go into temp Buildroot, who here, if you are used to compiling a kernel, there is make menu config. And now I can go through and I can easily start configuring things about my embedded system. So if I go into my system configuration and say, no, I don't want a init system, and yeah, give me a Getty, and change my system banner and host name, and oh, by the way, I would like to have useful things inside of it like links or netcat or socat, or what would be really great? Not having bin ash. I'd really like to have the full bash. And when I go through and I save my configuration, just like any kernel, I've got everything stored in one file. And when I say make and go through and actually compile everything, what it's doing there is unset curl and it will actually go through and retrieve all of the sources for all of the individual packages that I tell it to, and what it outputs is a tar file. Now, for everybody who knows, that's all that a Docker image actually is. All a Docker container is a tar file. So if I take this and I say cat rootfs tar, and I say docker load, oh, and this is going to be, I forget what the exact one, no, it's docker import. I have to tell it, hey, pull things in from standard input, and I'm going to tag this container as infracoders. Links. Yep. Is Dockerd running on my host? Dockerd is probably not running on my host. So what we will do is I'm going to back up a little bit. I'm going to take that, and I'm going to say, hey, scp temp build root output. Build root output images rootfs tar over to that host. So this is this 6 meg container. For those of you who have taken a look at the Docker Hub, where when you see things like this Nginx container, which they don't make it especially easy to find a lot of the sources on. If you know what you're looking for, this redirects into the right location of the Docker library, and we go through and take a look at something like Nginx. And then you have to go through and dig to get to the source. And then you have to pull up the version. And then you go in and look at the Docker file. You'll see that they start and they do things like, hey, first we're going to start with the Debbie and Jesse container, which is about 300 megs. Then we're going to run these apt-get update commands. Then we're going to remove some of the stuff and import GPG keys and do all this. And again, like Ram was saying, if you pull in code from the Docker registry, you're running other people's arbitrary code. You're trusting that whatever has been put up on the Docker registry is set. And I think that they removed the terminology, but they used to have a term called a trusted container. The only thing that a trusted container meant was that Docker retrieved the assets from GitHub and then compiled the image and pushed it up. So that means if I put, the Knight DOS tool inside of my image and then stuck it on GitHub first and then told Docker registry about it, they will very nicely compile my DDoS tool and then push it up on the Docker hub and leave it there, ready for me to pull down. So I have transferred this over to the host. I go back in. I now have it sitting here, and I have rootfs tar, and I can say cat rootfs. Actually, we'll say docker import help. And it says, hey, give me a URL or standard in and a tag. So I can say cat rootfs tar doc into docker import, and I want to call this, like I said, infracoders. Actually, we'll just say 1.0. Oh. Infracoders. What did I miss? Invalid repository name only. Well, so that is actually the tag on it. But we'll. Oh, okay. Great, awesome. So what I will do is I will say docker tag 3f1bcc as infracoders 1.0. And now when I say docker images, I see that I have my infracoders 1.0 image running. And if I say docker run-t-i infracoders bin bash, I have this BusyBox container, which is only 7 megs and has things inside of it like curl, so that I can make useful network calls directly from my ultra minimal container. Now, doubly why this becomes important is it's not like build root is actually this thing that's necessarily as stripped down as you think. maybe, like, they actually have a full package management system that you can build in, but, you know, if I want to run a mail server like Exum, or I want to run my bind server out of there, I can build it exactly for what it needs to be. So that whole promise of these ultra minimal containers to really do that one thing that you needed and not pulling in the kitchen sink, that's how you can get it done. And the other important thing here is when I go through here, and I'll actually back out of that one, I'll go back to Docker run, I'll do BusyBox again. Yep. Maybe I will do it correctly. Yep. Let's just get rid of that. So if I go through and I look at what Docker's providing me, because this is where I just started from, Docker pull BusyBox. You know, I'm again trusting what they're handing me, and I look at lib64, which is actually just lib. I don't have glibc in here. I have microlibc because that's what they decided was useful for me. Well, I don't want microlibc. Everything, I understand that glibc is really, really fat because, like we said, I understand that my BusyBox container isn't 2.4 megabytes, it's 7.8. But that's something I'm willing to live with, considering that the Fedora container was 370. It's that, oh, yes. I'm going to have a blog post up on the CoreOS blog within about a week and a half. You're basically seeing...
This solves my problem.
Yeah. What I will say is if you email me, I can send you a link directly to my config that I'm starting from, because I actually maintain it up on gist.github.com. Unfortunately, I should just make it a public one here. So, yeah, let me see if I can do that. Advanced options. Yeah, come on, edit. Can I make it public? Yes, make public. Congratulations! My config is now public. So if you go to gist.github.com/BrianRedbeard, the nice thing is if you untar build root and you stick that config into it and then run make menu config, you're actually starting from my settings. So then you can easily go through and say, yeah, it's cool that he did that, but I really don't want curl in there or other stuff. And the one that I've got up there is actually not the one that I started from here. Like this one is, so I'm using like really new versions of bin utils. A couple things there that you might need to know. So this was done for a Fedora 20 machine. So like GCC. So like the version of GCC on Fedora 20 is 4.9. So inside of build root, in your system configuration and your build options, it actually has things like GCC optimization, toolchain, that's what it was. So you can actually set, I want to build which version of glibc, I want to build which version, or I'm starting from what version of GCC. So it makes it so that you can really have it tuned really well, all the way down to, you know, like that BusyBox. So think about this one. We looked inside the BusyBox container, and they were linking in 32-bit libraries, but Docker only runs on x86-64. So it's just one more example of like they've really not gone through and tweaked that at all, which is why I spent a lot of time figuring. So the big thing to take away is a tar image is a Docker container. Like if you do a Docker export, it takes that and just slaps it out to a tar file. So
Is it the tar of the slash basically?
yes. Yeah, and it's going to expect the device nodes and everything to be in there as well. So if you're going to build that for, or like starting from a local directory, you're gonna have to like make nod and everything, which is one of the nice things about build root is it does all of that for you. One other thing.
I have a Linux host, right? Okay, I can just go to slash and tar out of it.
You could, yeah.
System.
You certainly could. You'll want to skip sys and proc because those are going to be provided by the host. The other nice thing here and this is something I'll cover in that blog post, is you'll see I have this directory called overlay. So one of the things that I found was, you know, two things. I use LL all the time, and that's not something that's set by default in the host, but their default profile knows about sucking in anything from profile.d. Additionally, like, I really wanted base64 in there. Base64 was not a package that they shipped. Well, base64 is a package shipped on my Fedora host, and I made sure that all of the shared libraries were going to match up with what I needed, so I didn't have to then go through and compile it, because I know that that binary complies with the contract from the Linux ABI, Application Binary Interface. I know that because that is compiled in such a way that all of the libraries that I'm going to be looking for are on that host, I can just copy the binary in and go. So I created this overlay directory, which, similar to what you were asking about, just kind of takes everything that's in there and throws it in from the root. And then in my config file, I specify that there will be an overlay directory starting at overlay. So I can easily just throw in arbitrary files without having to build some package that is knowledgeable about how build root works. So I will say I have gone all over the map. I have showed you a little bit of everything, hopefully just enough to be dangerous. Yes?
So, what about several compatibilities on the host and the containers, etc.? Does it matter or it doesn't matter in the window?
Repeat the question one more time?
Kernel level versus kernel version of the host versus the
Okay.
container and all the things that we are building in.
So, one of the dirty secrets that companies like my former employer Red Hat do not want you to necessarily actively think about is the kernel does not break user space. The kernel keeps a consistent ABI. If I go through and so let's take a look here. So I'm running this Fedora machine, and this is an actual Fedora machine. I run uname-a. My kernel is 3.15.10. I go into my docker run -t-i-rm Fedora bin bash. I go into this Fedora container over here. I run uname-a. It's running 3.16.2. The reason that it's running 3.16.2 is because CoreOS is running 3.16.2. If you have a binary that is compiled against a certain version of glibc, and glibc is available on that host, it will run. If it's a statically compiled binary, even better. You don't even, there are no dependencies. What Red Hat has been selling you is this bill of goods where they are backporting patches into an old version of the kernel to provide stability. I personally trust that kernel.org's kernel, the stable tree, is stable. And running an old kernel is not directly providing me any additional security mechanism. Yes?
I guess container does not use
Yes. Yes, to answer that, the container is using the kernel from the host. There is only one kernel on a system.
That's the idea behind containers, right?
Bingo. Yes. If you wanted multiple kernels, you would run virtual machines on top of a hypervisor. Yep. Exactly. So,
So maybe now is the time like to see if people have some other questions.
yes.
So-
I mean, that's the thing. I could just keep going on and on and on with this, but I assume that eventually some of you want to go home. So, yes.
Besides, hoping to hear more about the fleet, how does it manage the resources and stuff? What kind of scheduling do you do?
Okay, so Fleet is a very basic optimistic scheduler. It's not designed to replace like Aurora or Marathon inside of Mesos. You also have to remember that Fleet was written before things like Kubernetes existed. So we are actively working on Kubernetes. We have folks who are committers on the project, and you can expect to see Kubernetes directly integrated into CoreOS soon, because it's a natural evolution of what we were trying to do with Fleet.
Possibly to run Mesos in CoreOS?
Yes, it is. There is a gentleman by the name of Tim Nollett, who is very, very brilliant. He had a presentation that he gave. Nope, that's not Tim Nollett. He works for a company called Magnetic.io. That was the Stampede one. There's Tim Nollett linked. Maybe Google will provide. But he actually has a walkthrough on setting up CoreOS inside of no, was it up here? Oh, Mesos on CoreOS. Yeah. So github.com/tnolet. And he actually has the Docker files, and I believe he has a CloudFormation template and a actual cloud config YAML file, which will go through and deploy everything, I believe, to Fleet.
So this is a fleet concept of Mesos before scaling.
Well, so the case of this one is Fleet is just there to guarantee that the API endpoint is up and running somewhere, and I believe that the Mesos slave is running on all of the hosts. So Fleet's just there to guarantee that your infrastructure components are up and running, but then all of the scheduling and decisions beyond that are made by Fleet itself, or are made by Mesos, and then the scheduler inside of Mesos. Yes?
So for best practice, the things that communicate via dbus, if we run them in containers, should we route dbus into the containers somewhere?
So that's one where realistically you're going to be better off once KDBus lands, because then dbus will be available inside of the kernel directly. I have never directly tried to expose dbus into a container, but I know that folks from our side have done it. So I can't give you a really good answer to that of saying as a best practice. I mean, if you need to talk to dbus, yeah, you should probably expose like the dbus socket. To give a orthogonal answer, but does have, you know, a marginal amount of overlap. If I needed to run a container that controlled all of the containers on a host, I can bind mount that Docker socket into the container. So I can say var run docker.sock, and I'll just say run infra coders. Oh, come on. Bin bash. So at this point, if I take a look at var run, oh, what happened? Docker run -v var run docker.sock var run docker.sock. Oh. Let's just expose it into root. Ah, strange. For some reason, it wasn't presented in to the var run location, but you can actually then bind mount things like sockets from one container into another. So if I, took this and fired up SOCAT to read off of one socket, I can create a socket in one container, expose it out to the host, bind mount it into a second, and do a TCP type communication or a streamed communication without ever using TCP or without having those hosts go over the network themselves. So you can very explicitly define the IPCs for how two containers would talk to each other. So knowing what I do about that, that's where I loop back and say, yeah, you should be able to talk to dbus from inside of a container. You just need to explicitly define that IPC so that the container will be able to see it.
Just not a -v.
Yep, exactly. You're up.
So I can easily visualize Docker being used for processing and computing and stateless thing,
Mm-hmm.
how is usually data and container, like code and data separation recommended, or how do people usually use it?
So one of the things that I personally prefer to do, so Docker has a concept of what they call a data volume, but the data volume is just another container, and your files are trapped inside of that container. So personally, I like doing things more like, let me say, so I'll do this, I'll spawn the same container again. I'll say -v mkdir var infracoders sudo mkdir sudo chown. Actually, that's good enough. And then I can say pass in var infracoders as with just the path infracoders. And now inside of this container, I have some long-running process that goes into my infracoders path for x in sequence 1000 do touch x dot that done. So, you know, I go through and I create my 1,000 files that are sitting inside of this directory, and then from, if I go back to, now that I've exited out of that container, var run or var infracoders on the host, all of those files are actually there. And yet, if I do a docker ps, that container that was creating that data is gone. It reaped itself because I had this. No, it did not actually reap itself. So that's one other thing. The docker-a. So this was actually my one, but had I run that with --rm, the container would reap itself, but the existing files that it created would still be sitting on the underlying host, which means a few things. One, if I needed to back those up and the container was still online, I can copy the files out without having to enter into the namespace for that container. It also means that I could bind mount that volume into a second container so that they could collaborate on the files at the same time. Maybe I've got one file or one container that's a batch job creating output files, and then another file that's an HTTP presentation container that has Nginx like serving them out to another component. Yes?
Follow-up question on the same thing.
Yes?
This file inside the container, is it like a point for a container, or is it separate?
So it's an actual bind mount into the container when you specify a -v in that case. Well, because I specified a -v and then a like path on the host :path inside, it does it as a bind mount, which is how it actually presents it in there. Now, if I had a second container that was consuming that data, and I wanted to make sure that it did not do anything to it, I can suffix that with a :ro for read-only, and now this other container, which is looking at this and consuming all of this data, doesn't actually have any of the permissions.
All the writes are right through, or
Yes, they're right through.
all right?
Yes. I mean, it's one kernel, so in that case, it's still using the same, because it's not a part of that mount namespace directly. It's been passed through.
The container can cache it inside the well, not.
Yeah.
If we use NFS, right? So we cannot do this to containers in other hosts.
No, you cannot do it to. What was that?
It's a real file.
Yes, it's a real local file system. If you wanted to do something like that, you can. So let's say if I had an NFS mount on here, I could then bind mount a portion of that NFS mount in, and then it would be present for all of the all containers running on a series of hosts that had that NFS mount presented.
The follow-up question.
Yes.
Can you expose the block device to the container?
Yes, you can. So that's one thing. So I'm inside of this container. What is it? So what's going on here? that case, I probably have to do privileged. But so that's how, for example, with that when I was saying before that wrong location. When I was saying that one customer that I was working with was modifying the firmware on the HBAs with the HP Smart Array utilities, that's how they were doing it. They were talking to the raw devices from inside of the container.
So it's the same minus B.
No, in that case, because they weren't presenting the device all the way through, but it was the same kernel, they were running a make nod of the correct major and minor device inside of that. But it had to be a privileged container in order to run the make nod to be able to then talk to the underlying physical component.
As long as you link those nodes from the container to actually get to
The raw device, yes. Yes, that's definitely the case.
Make not from outside into the namespace using the namespace. Execute the command.
Yes, you could. So if I ran an NSEnter to enter into that namespace for those and ran them kind of out of band, yes, you could definitely. Yes. Yeah.
So if you were to take a LUN and mount it into a container, you'll do it as a host first and then give it the file system?
If you want it to be an unprivileged container, yes. If you don't mind it being a privileged container, then a privileged container has sysadmin, which is the Linux capability that it needs to actually do the mount itself.
Can you customize it?
Yes. So.
This is per container.
Yes.
Container, this
See.
root will have a little more than the other.
Yes. So you can specify on a container by container basis specific privileges that you want to add. So you could do that in such a way where you selectively pick and choose. The only thing that I would mention with that is keep in mind that in the same way of like writing an SE Linux rule where one rule might say allow stat and another one allows read, and if you're troubleshooting it's like can't complete, needs stat. Then you go through can't complete, needs read. You need to compose all of the various permissions that you might need to make a file system, mount the file system, do all of that stuff. So it's not to discourage you, just to be like keep that in mind when you go to do it, that there may be additional things that you need to grab.
I have
Yes.
just want to go back to my earlier question, right?
Uh-huh.
How do you find if a node crashes that is not part of the quorum?
Okay, so in this case, a machine can be involved in that etcd quorum via fleet, a machine can be a part of the etcd cluster via fleet without participating in consensus. Because fleet D running on the host is writing out to that remote etcd cluster saying, this is who I am, this is the units that I'm running, and then other nodes there that are running fleet D and remember that same cluster can recognize if that node goes away and spawn that on an additional host to make sure that it comes back.
This is like an indirect heartbeat that's going on from every node to the etcd cluster?
Yes. Yes.
So even though I'm not doing anything, then there is this continuous chatter going on in the whole cluster.
Yes.
In the 500 nodes, probably all nodes are writing to this 5 node.
Yes.
And what is that frequency? How frequently is it?
For fleet, I don't actually know. I think it's tunable, but I don't know off the top of my head. And that's one where, yes, in that case, if you're trying to run a 500 node fleet cluster with 9 etcd nodes, there's going to be a lot of traffic, and it's probably going to be slow. In that case, yes.
That's good.
Yeah.
Another thing is, right, okay, this is more of a proactively, the fleet daemon is writing to the etcd for
Yes.
some key value. Right?
Mhm.
So if the node crashes, then it will stop writing this. Right?
Yes.
So that's a hint to the rest of the folks that this node has come from. Right?
Yes,
Okay.
that's correct. Yeah, so, while you can use this to coordinate 10,000 machines, it is, no matter what, running 10,000 machines is non-trivial. What we're trying to do is make it easier and to make sure that you have the tools available to get from A to B. But invariably, there's going to be things like Mesos that are going to make that easier for you because you want to end up treating this entire group of machines as just some compute pool so that you can treat it like a utility where you can say, I need to run 30 copies of this and 25 copies of that, or I want to run on this class of machines this primary function, and then I want you to run this secondary function to use any of the slack. So one of the things that Google has talked very publicly about is they have entire groups of machines where the primary focus of them is to run search. Like those machines, that's what's making money, is, you know, the AdWords kind of content going on there. But then none of those machines is necessarily using 100% of their resources. So then they run MapReduce in the Slack area so that then they can have these other type of batch jobs doing additional work for them, so that they're really squeezing every drop that they can out of the compute resources that they've got, but without having to necessarily say, you host, I want you to be called this thing, and I want you to run like XMPP and, you know, web search and Elasticsearch. Like they kind of float around and
Nicing.
the what?
They're nicing it.
Yes. Yeah. At an entire container level. Yeah.
One related question is, if all these say 500 nodes in your cluster, right?
Uh huh.
They are frequently, say every few seconds, probably writing the status of each of the apps, each of the services.
Yep.
To the HCD cluster. Is it gonna choke the HCD cluster, right? Or they're writing this
Yes.
with the timestamp.
Yes, that's why I was saying, like, if you're trying to run a 500 node etcd cluster and 500 nodes in Fleet, you're going to start seeing performance.
500 node HCD cluster. HCD cluster is only 5 nodes.
Yeah. Yes. You're when you start trying to have 500 nodes participate in that one cluster, you're going to see performance decreases. And that's why I was also saying, like, the size of the keys matters. So where the ultra minimal container comes in is I was actually building that because there's an additional thing that I have been working on. It's called StretCD, where the whole purpose here is it's just this super simple shell script that's going through, I just can't win in making it readable. It's going through and using curl and a combination of reading from dev urandom and then piping that through base64 to then just generate random strings of data so that I can write arbitrary key lengths into etcd. So this is what I've been using to say, what does it look like when I write 100,000 keys that are 10 bytes each? What does it look like when I write 100,000 keys that are 1 meg each? And run through and be able to have a consistent test framework so that now I can then take that and run it on EC2 and on Rackspace and on GCE and on bare metal and go, what do the performance numbers actually look like? What does it look like in a 5-node cluster? What does it look like in a 3-node cluster? What's it look like in a 30-node cluster where 9 nodes are in consensus and everything's going wild trying to write these giant keys? Like, I wanted to generate a consistent set of numbers that could then be plotted out so that folks can actually, rather than going, what do you think? They can then take this on their hardware and go, no, this is what my performance profile actually looks like.
And does CoreOS maintain the same time on all of these 500 nodes?
We run NTPD, so hopefully, yeah.
It's issues, right?
Yeah, I mean, so as far as that, we're actually spinning up NTPD by default, and in Etsy ntpd.conf, we have it set to use the generic pool. So one thing that I would say there, and I'll leave this as the last kind of closing idea, and then we'll get out of here since it's after 9. So if you go and look in here, you'll see most of these files, or a lot of the files, are symlinks over to userlib. Systemd creates these symlinks in the event that files are not there. So this is just so that we're pulling in information off of these read-only file systems so that there are sensible defaults. If you want to change it, it's as simple as doing a read link to find out, you know, what the NTP configuration is actually coming from. and remove that link, copy the file into place. Again, sudo is your friend. And now I can go through and I can make, again, if I had paid attention to what I was doing, I can go through and I can make changes to that configuration so that I now have that override. You know, I can do things like that and override my resolve conf and all these kind of default files. It's just we do that so that there is a sensible something there. In the long run, what we are doing, and we're about 90% of the way done this, is that all of the state, all of the thing that defines this particular system as being this system is defined outside of that read-only directory. And the idea is that you will be able to do if I can spell preserve correctly. You'll be able to do that, and you notice it can't remove the stuff in the read-only file system, but all of the stuff in Etsy and everything else it will successfully remove, and then if you reboot that machine, it's a fresh install. You basically took this clone, shot it in the head, and reset it back to 0 so that when it comes online, it recreates all of those files back to an empty state. That's the idea of where we're going with that. Yes?
Let's just,
Oh.
let's just
Okay.
Ryan.
Like I said, I can keep going. So.